Very good afternoon to everyone. Today I'm going to present with my presentation title, that is AI powered VLSI transforming chip design for the next generation. So in this presentation I'm going to discuss about the transformative impact of artificial intelligence on very large scale integration design. Here I am going to cover the limitation of traditional VLSI design flow, the rise of AI in chip design, specific application of AI in various stages of the VLSI design process, available in EDA tool with AI capabilities, then industry adoption, future trends, challenges, research opportunities, and the overall impact on the semiconductor industry. In my presentation aims to the highlight how AI is enabling faster, smarter, and more efficient chip design cycles, and emphasize the importance of VLSI engineers mastering AI tools for the future semiconductors. Now, why VLSI matters now more than ever. So very large scale integration is the process of integrating hundreds of thousands or even millions of transistors on a single chip. This technology has been the backbone of the electronics revolution, enabling the creation of powerful and compact devices. In today's world, the demand for smaller, faster, and more energy efficient chips is constantly growing and making VLSI more critical than ever. Here, I have explored the reason why VLSI is of paramount importance in the current technologies landscape, focusing on the increasing complexity of applications such as artificial intelligence, the Internet of Things, and 5G and 6G technologies. Now I am discussing point by point. Number one, the foundation of modern electronics. So basically, VLSI is the cornerstone of modern electronics. It allows for the integration of complex system onto a single chip, reducing the size, cost, and power consumption while increasing the performance and reliability. Without VLSI, many of the devices were relying on daily, such as smartphones, then laptops, then advanced medical equipments would not be possible. The point number two is enabling complex system on a single chip. VLSI enables the creation of complex systems on a single chip by integrating a vast number of transistors and other components. This integration this integration reduces the physical size of electronic devices and improves their performances by minimizing the distance signals need to be traveled. VLSI reduces the signal delays and power consumption, leading to faster and more energy efficient devices. Point number three, reducing size, cost, and power consumption. One of the primary advantage of VLSI is its ability to reduce the size, cost, and power consumption of electronic devices by integrating more components onto a single chip. VLSI eliminates the need for multiple discrete components, reducing the overall size and cost of the devices. In additionally, VLSI reduces the power consumption by minimizing the distance signals need to travel, leading to more energy efficient devices. Point number four, that is increasing performance and reliability. VLSI also increases the performance and reliability of electronic devices by integrating more components onto a single chip. VLSI reduces signal delays and improves the overall speed of the devices. Additionally, VLSI improves the reliability by reducing the number of interconnections between components which are potential point of failure. The next point is driving innovation in emerging technologies. The increasing complexity of the applications such as latest trending technology like AI, IoT, then 5G, 6G technologies drives the need for advanced VLSI design. So this technology requires chip that can process vast amount of data quickly and efficiently, which is only possible with the advanced VLSI techniques. Now, the just now I told these three technologies are now booming in this era. That is artificial intelligence. Actually, AI application is such as machine learning and deep learning concept require massive computational power. So VLSI plays a crucial role in enabling AI by providing the hardware necessary to process the vast amount of data required for the applications. In advanced VLSI design, such as specialized AI accelerators, are essential for improving the performance and efficiency of AI systems. Number two, there is Internet of Things. So the IoT, Internet of Things, involves connecting billion number of devices to the internet, each generating and processing data. VLSI essential for creating the small, low power chips need for IoT devices. So these chips must be able to perform complex tasks such as data acquisition, then processing and communication, while consuming minimal amount of power to extend battery life. The another latest technologies, 5G and 6G technologies. So 5Gs and 6Gs technologies requires high speed data processing and communication capabilities. So VLSI is a critical for developing the chips needed for 5G, 6G infrastructure and devices. These chips must be able to handle the high data rate and low latency requirements of these technologies, which require advanced VLSI design and manufacturing techniques. Now come on to the next slide. The role of VLSI in specific applications. So VLSI impacts extend to the various specific applications, each benefiting from its unique capabilities. First one is consumer electronics. In consumer electronics, VLSI enables the creation of powerful and compact devices such as smartphones, then tablets and wearable devices. These devices require chips that can perform a wide range of tasks, from processing user input to displaying high resolution graphics, all while consuming minimal power. Number two, in automotive industry. The automotive industry is increasingly relying on VLSI for advanced driver assistance system, that is ADAS system. It is a new technology. Then autonomous driving and electric vehicle control system. This system requires chips that can process sensor data, make real decisions and control vehicle functions, safety functions safely and reliably. Then in another application is specific application in healthcare domain. So in healthcare, VLSI is used in medical imaging devices, then diagnostic equipments and implantable devices. So these applications are required chips that can process complex data, provide accurate results and operate reliably in critical situations. Then another application is aerospace and defense. The aerospace and defense industries rely on VLSI for mission critical applications such as navigation systems, then radar systems and communication systems. This application requires chips that can operate in harsh environments, withstand extreme temperature and provide high level of performance and reliability. Coming to the next slide, AI plus VLSI, it is a new design paradigm shifts. So AI actually offers solution to overcome the limitation of traditional VLSI design methods. AI can automate and optimize various stages of the design flow, leading to significant improvements. And this paradigm shifts is crucial for meeting the growing demands of the semiconductor industry. This shift has several important implications. The first implication is increased automation. So generally AI enables greater automation of the VLSI design process, reducing the need for manual intervention and freeing up designers to focus on more creative and strategic tasks. Number two, there is improved design quality. AI can lead to improved design quality by exploring a wide range of design options and optimizing the design for various performance metrics. Number three, reduced time to market. AI can significantly reduce the time to market for new VLSI products by automating and accelerating various stages of the design flow. Then number four, that is lowering design cost. AI can lower design cost by reducing the need for specialized expertise and automating time consuming tasks. Number five, that is enhancement innovation. So AI can enable designer to explore new and innovative design ideas that would not be possible with the traditional design methods. Number seven, that is democratization of design. So AI power tools can make VLSI design more accessible to a wider range of engineers, even those without specialized or expertise. Coming to the next slide, the limitation of the traditional VLSI design. So in traditional VLSI design relies heavily on the manual process and it is a rule-based algorithms. While these methods have served the industry well for decades, they are increasingly struggling to keep pace with the growing complexity of modern integrated circuits. Some key limitation I'm going to highlight here. Number one is the increasing design complexity. The first one is increasing design complexity as the number of transistors on a single chip continues to increase. The design space explores the exponentially. So this makes it difficult for human designer to explore all possible design options and find the optimal solutions. Number second limitation, that is time consuming design cycles. So manual design process are inherently slow and iterative. So each design iteration requires significant time and effort, leading to long design cycles and delayed time to market. Number three, that is suboptimal solution. So most of the uh, AI algorithms are rule based, often relying on heuristics and approximation, which can lead to suboptimal design solution. So this solution may not fully exploit the available design space or achieve the desired performance targets. Number four, that is expertise dependency. So traditional VLSI design requires highly sophisticated, specialized expert in various domain such as circuit design. There are different types of circuit designers are required for yeah, integrated circuit design, like analog circuit design, then digital circuit design, then combination of analog and digital, that is called mixed signal circuit design. So different experts are required in that particular domain. Then that means it is fully depends on the expert dependent. Then layout is another domain, and verification of the circuit also another domain. We need different expertise in that particular field. So this expertise is become increasingly scarce and expensive. Then verification, last one is verification bottleneck. So verifying the correctness and performance of complex VLSI designs is a major bottleneck in the design flow. So traditional verification methods such as simulation and formal verifications are becoming increasingly computationally expensive and time consuming. Now coming to the slide number 6, that is AI driven solution for VLSI design. So AI actually offers a powerful set of tools and techniques to overcome the limitation of traditional VLSI design methods by automating and optimizing various stages of the design flow. AI can lead to significant improvements in design quality, then time to market and cost. Some key applications of AI in VLSI design include, that is, high level synthesis. So high, high level synthesis, that is one important area. So AI can be used to automatically generate RTL, that is called register transfer level code, from high level specifications such as C++ or system C or system Verilog programming. So this can significantly reduce the time and effort required for RTL design and verification. So AI algorithm can explore the different architectural options and optimize the generated RTL code for performance and power and area. Then next AI-driven solution is placement and routing. So AI can be used to optimize the placement and routing of the transistors and interconnects on a chip. So AI algorithm can consider various design constraints such as timing, power, and congestion to find out the optimal placement and routing solutions. This can lead to significant improvements in chip performance and density. Then reinforcement learning is the particularly useful in this particular domain, in placement and routing area. Then circuit optimization. So AI can be used to optimize the performance of the individual circuits such as amplifiers uh, uh, and comparators. Not only amplifier comparator, there are so many different circuit options are there. So AI algorithm can automatically tune these circuits parameter to achieve the desired performance target and such as gain, then bandwidth and power consumption. So that is another solution. Then another next one is design space exploration. So AI can be used to explore the vast design space of VLSI circuits and identify promising design options. AI algorithm can learn from the past design experiences and predict the performance of new designs, allowing designers to quickly evaluate different design alternatives. Then fourth number is the verification and validation. This is also another area, AI-driven solution, that is verification and validation. So how AI can be useful in this particular domain? AI can be used to improve the efficiency and effectiveness of the VLSI verifications. Generally, AI algorithms can automatically generate the test cases, then identify the potential design errors and accelerate the simulation process. Then machine learning actually model can be trained to detect the anomalies and predict the failures, improving the overall reliability of the design. Then fifth number is power estimation and optimization. So AI can be used to accurately estimate the power consumption of VLSI circuit and identify the opportunities for power optimizations. AI algorithm can also analyze the circuit behavior and predict the power consumption under different operating conditions. So this information can be used to guide power optimization techniques such as clock gating and voltage scaling. Then next one is analog layout automation. So this is also another AI driven solution, how AI can contribute in VLSI design domain. So analog layout automation is also another part. So AI can automate the layout generations of analog circuits as a traditional or manual process is a time consuming steps. So AI algorithm can learn from the existing layouts and generate the new layouts that meet the desired performance specifications. So this can significantly reduce the design time and improve the quality of the analog layouts. Now coming to the slide number 7, that is rise of artificial intelligence in chip design. So in this slide, actually, I have covered that how AI, particularly through machine learning, then deep learning and reinforcement learning, is enabling automation, enhancing pattern recognition, then facilitating prediction and optimization, and improving the decision making process within the complex landscape of chip design. The first one is AI for automation. You can see I have considered total four characteristics and four areas. One is in AI, artificial intelligence, then machine learning, deep learning, and reinforcement learning. So the main our main focus, first one is AI for automation. How AI can contribute for automation. So you can see first four ES sign is given. You can see automated layout generation, then automated verification, automated test generation, then high level synthesis. All are, you can see, these are the ES. That means how AI can help to in this particular area. So AI actually offers a powerful solution by automating the various stages of the design flow, leading to significant improvement in efficiency and productivity. The first one is automated layout generation. So what is how AI can help to generate to automate the layout generation with the help of AI algorithm can automatically generate and optimal layouts for circuit components considering factors such as area, performance, and power consumption. So this reduces the reliances on manual layout designer and accelerates the design cycle. Then next one is automated verification. AI can automate the verification process by identifying potential design flaw and inconsistencies, ensuring that the chip meets the required specification. So this reduces the risk of costly errors and improve the overall quality of the design. Next one is automated test generation. AI can, in this particular domain, AI can automatically generate test patterns to thoroughly test the functionality of the chip, ensuring that it operates correctly under the various conditions. So this reduces the time and effort required for manual test generation and improves the of the testing process. Next one is high level synthesis. So AI can be integrated into high level synthesis tools to automatically translate high level description of chip functionality into hardware implementation. This allows designer to focus on the architectural aspects of the design rather than the low level details. Now next one is machine learning for pattern recognition, that is comes under second category. So machine learning excels at the identifying pattern in large data sets, making it invaluable for various tasks in chip design. The first one is the defect detection. So machine learning algorithm can be trained to identify patterns indicative of defects in chip manufacturing, allowing for early detection and prevention of yield loss by analyzing data from various sources such as optical inspection and electrical testing. Then ML model can learn to distinguish between normal variations and actual defects. Next one is anomaly detection. So machine learning can be used to detect anomalies in chip behavior such as unexpected power consumption or uh, performance degradation. So this can help identify potential security vulnerabilities or hardware failures. Then coming to the next point is that is design rule checking. So DRC stands for design rule checking. So machine learning can assist the in DRC by learning to identify learning to identify patterns that violates the design rules even in complex complex and no-sense cases. This can improve the accuracy and efficiency of DRC, reducing the risk of manufacturing errors. Coming to the next slide, the IP reuse. So machine learning can analyze existing IP blocks to identify reusable components and patterns, facilitating the development of new chips by leveraging existing designs. This reduces the development time and cost. Then third one is deep learning for prediction and optimization. So under this category, I will explain one by one, step by step, that deep learning is a subset of machine learning. I think everybody knows, which offers even greater capabilities for prediction and optimization due to its ability to learn complex hierarchical representation of data. First point is performance prediction. So deep learning model can be predict the performance of a chip, electronic chip, based on its design parameters, allowing designers to optimize the design for specific performance targets. So this can significantly reduce the need for costly and time consuming simulations. Then next one is power estimation. So deep learning can accurately estimate the power consumption of a chip, enabling designers to optimize the design for power efficiency. So this particularly important for mobile and embedded devices where power consumption is a critical constraint. Next one is routing and optimization. So deep learning basically can optimize the routing of wires on a chip, minimizing wire lengths and congestion, which can improve the performance and reduce the power consumption. Then next one is placement and placement optimization. So deep learning can optimize the placement of circuit components on a chip, minimizing wire length and improving signal integrity. Then last one is process variation modeling. So how deep learning can useful for process variation and modeling. So deep learning can model the impact of process variation on chip performance, allowing designer to create more robust design that are less sensitive to manufacturing variations. Then last one is uh, reinforcement learning. So how reinforcement learning is useful for decision making in our in VLSI chip design. So reinforcement learning is a type of machine learning where an agent learn to make a decision in an environment to maximize the reward. So this is a particular useful for tasks that involve sequential decision making, such as floor planning. So how reinforcement learning is useful in floor planning. So RL can be used to optimize the floor plan of a chip, determining the optimal placement of different functional blocks to minimize wire length and congestion. The reinforcement learning agent learns by exploring different floor plans, configurations, and receiving rewards based on the resulting performance matrices. Next is power management. So how RL can be useful in power management? RL can be used in to develop intelligent power management strategies that dynamically adjust the voltage and frequency of different chip components to minimize power consumption while maintaining performance. Next point is adaptive testing. So how adaptive testing is useful in RL? So RL can be used to develop adaptive testing strategies that dynamically adjust the test patterns based on the results of previous tests, improving the efficiency and effectiveness of the testing process. Next one is hardware Trojan detection. So reinforcement learning can be uh, uh, reinforcement learning can be used to detect the hardware trojans by learning to identify pattern of behavior that indicative of malicious activities. So the RL agent can learn by observing the behavior of the chip and receiving the rewards for correctly identifying the trojans. Coming to the next slide, that is future trends and challenges. While AI is already making a significant impact on chip design, its potential is far from fully realized. So several future trends are expected to further accelerate the adoption of AI in this particular field. So I will highlight few points, that is increased availability of data, then advancement in AI algorithm, then cloud-based design platforms, then integration of AI into EDA tools, then generative. Coming to the last one is generative AI. So the point number one, that is increased availability of data. The increasing availability of data from past chip design is providing a rich training ground for ML algorithm. Then the second one is advancement in AI algorithm. Ongoing advancement in AI algorithms such as deep learning and reinforcement learning are enabling more sophisticated and powerful AI-based design tools. Then third number is cloud-based design platform. So cloud-based design platforms are making it easier for designers to access and use AI-powered tools. Fourth number is integration of AI into EDA tool. So EDA stands for electronic design automation. Most of the EDA vendors are increasingly integrating AI capabilities into their tools, making it easier for designers to incorporate AI into their workflows. Then last one is generative AI. So generative AI models can be used to create novel chip architectures and designs, potentially leading to breakthroughs in performance and efficiency. However, there are also several challenges that need to be addressed to fully realize the potential of AI in chip design. The first one is the data quality and availability. The second one is explainability and interoperability. Then integration with existing workflows. Then computational resources. Then security concerns. Then ethical considerations. So these are the points we need to address. These are the future challenges in this particular area. Now, coming to the conclusion. So, in this slide, I'm going to discuss about the AI transforms uh, chip design for faster and better, cheaper chips. So AI has the potential to revolutionize the field of chip design, enabling faster design cycles, improving performances, and reduced cost. While there are challenges to overcome, the increasing availability of data, advancement in AI algorithms, and integration of AI into EDA tools are paving the way for future where AI plays a central role in chip design. By addressing these challenges and embracing the opportunities, the chip design industry can unlock the full potential of AI and create a new generation of high performance, energy efficient, and reliable chips. The future of chips design is inextricably linked to the advancement and adoption of AI technologies. So, thank you very much for this discussion and this presentation. Thank you.